All right, so here is chapter 8.6, counting and permutations. So this is going to give us a good idea of the possibilities we might encounter, the number of possibilities we might encounter in certain everyday scenarios. So the fundamental counting principle, this is what everything else is going to be based off of. Here we can look at an example. Here they tell us that a store sells 6 models of running shoes, okay, and offers each pair in a variety of 3 colors. Now, we might want to know how many different pairs of shoes then are available. So obviously for inventory reasons, just because you only shop at a shoe store that has, 80 different shoes, who cares? But we basically want to figure out what the total number is. So we could go ahead and say, well, we have 6 models and 3 colors, okay? And what we're going to end up doing is multiplying, but I wanted to kind of show an example here, and I wanted to kind of make it clear. So this would be an example of 6 blue shoes, right? Or the 6 different models. So model 1, model 2, model 3, model 4, model 5, and model 6. And the idea is that if we continued on, well, we could have all 6 of those models, model 1 in green, 2 in green, 3, 4, 5, and model 6 in green as well. And then we could do that for one more color, for example, red, like my shoes. Okay, 1, 2, 3, 4, 5, 6. And while these diagrams can be useful, it's not something we would generally want to do. So there is an actual rule for this. And when I say generally we don't want to do it, drawing a picture or drawing a diagram is a great way to get an idea of what you're looking at. So the actual rule is that if a selection can be made in M ways, okay, so in other words, we have M types of shoes, or M models of shoes, okay, and a second selection, so for example, the color, there's N colors, okay, can be made. The number of ways the 2 selections can be made is M times N. Now this works for more than 2 events. So for example, if we had this many models, this many colors, and then we have 12 sizes, we could just multiply M times the number of colors times the number of sizes, and that would tell us the total number of shoes that we would have available. Right? So for example, if we had something like how many outcomes can there be from rolling 2 dice, we're going to look at each dice individually, or die individually, right? So one die, there are 6 possible outcomes, and that's in the first die here. Well, on the second die, there's also 6 possible outcomes. So we're just going to go ahead and multiply those times each other. Okay, so this is die 1, that's the total number of outcomes. This is die 2, that's the total number of outcomes. And we would multiply and times each other. There would be a total of 36 different outcomes that could come from rolling 2 dice. Now, permutations are something that's a little bit different. So it's an arrangement of N elements in a definite order. So obviously, when you're rolling dice or you're picking out shoes, the order that you pick them out doesn't matter. You can pick red first, blue first, or the I think green was the other color I had up there. It doesn't matter. But if you have something like a situation like this, where maybe you have and I forgot to put the last piece up here, but let's say you had 5 people that you wanted to put in line, and the order of it mattered because you want to make sure that it's it's a good order in general, or I'm sorry, that you can keep track of the order, for example. So if you wanted to figure out how many ways you can put 5 people into a line, well, you think of it, your line would be like these 5 boxes, right? And so if we take person number 1, well, when we start with that first person, there's going to be 5 different options, right? So we have 5 possible outcomes for person number 1. Now let's say we put him here. It doesn't matter where we put him. If we put him there, 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 or there, or there. Either way, what we're going to wind up with is person number 2 will have 1 less box available to him. So when we get to person number 2, there will be 4 people. And again, this is just following the fundamental counting principle. Now we move on to person number 3. Okay, so let's say we put in person number 2 right here. Now it doesn't actually matter where we put them necessarily. Okay, so if we want to do that, and hopefully you can still see me, stupid motion center sensor just went off. So person number 3, we would just go ahead and toss right in here. Okay, because for person number 3, there are 3 boxes left. And then we just go down the line, and hopefully you're realizing what this looks like. Person number 4 would only have 2 options, and then the last person would only have 1 option. So hopefully you notice that what this actually is that if we want to find the number of permutations on objects, in objects, we just take the factorial of it. And so we see that if we wanted 5 children to be lined up in a row, we take 5 factorial and it tells us the answer. Okay? Now, we could also have a number of permutations that are part of a set. So basically, we have a situation where we have in people, okay, but we want to line them up in a smaller row. So we'll look at an example. But go ahead and get this definition down. If you got this down, you can look at the next example, but that's all that I'm going to ask is that you have all the definitions down, formulas for tomorrow. But the basic idea here is that this is the number of elements in the set, okay, in is. And then the number of elements that are used for a permutation is going to be R. And then lastly, we can look at how this would work in an actual example. So how many ways can 10 books be placed on display where there is only room for 4? So in this case, the number of elements, okay, or in, well, there's a total of 10 books. Okay, the number of so the number of elements that can be used in each individual permutations, well, that would be 4 because we only have room for 4 books. Okay, so we plug those values in, and the formula pretty much takes care of everything for us. So we just replace in, okay, we replace in with 10 because that's what n is equal in this particular equation, or this particular problem, and then we replace R with 4. Since there's only room for 4 books, we plug in those values, and we wind up with that there are 5,040 combinations when we have 10 books and only 4 spots to put them in. Okay? Please do come in with any questions tomorrow. I'll look forward to seeing you.